Okay. So we'll get onto the next section here, which is section 2.6. Okay, so we had vertical asymptotes. So we're going to do horizontal asymptotes. Asymptotes. Also, same idea, limits at infinity. Okay. So we've pretty much been able to take every kind of limit, right? We've covered really every kind of limit, except for what? There's one that we haven't covered. Okay. Suppose we have f of x. That looks like this. So another kind of limit that we could take is that the limit as x goes to infinity of f of x. Right, so what does this mean? This means that what's happening to the y values if x gets large, right? So x is not approaching a number. We just want to get a pattern. We're looking at these y values. So like here's x is 1, y is here, x is 2, y is here. But we want to get the pattern when x is getting really, really large. So what's happening to the y values if we look really, really large? Now, my paper, I don't have an infinite paper. So that's the problem. If I have an infinite paper, I could just draw everything, the whole thing. Right? But we're just looking for a pattern. Right? What are the y values approaching? 0. 0. Right. Let's see. We have Sandra. Yeah, so what we say is that the y values are going to 0. Y values are going to 0. Now, we haven't done that before. We've had the y values go to infinity, right? When x is approaching a number, but we've never had x go to infinity. Okay, so when this happens, so we say y equals 0 is horizontal asymptote. So HA, abbreviation. So VAHA. Ha, basically ha. Remember it by ha. Horizontal asymptote. Okay. Okay. That's when x is getting really large. I could also look at what happens if x is getting really small. So x is getting large means you're looking at the very right of the graph. I could also look at limit as x goes to negative infinity. And just to make it interesting, let's make it, let's say, even a different value. So let's say I tweak this. Of f of x. Okay. So now what's happening to the y values? We'll cross this out a little bit. As x is getting really, really negative, like super negative, what's happening to these y values? getting closer and closer to 1. Right? So then the limit as x goes to negative infinity, we're going to say is 1. Right? So still limits are predicting a pattern, but here we're predicting like end behavior. We're predicting what's going to happen when x gets really large and what's going to happen when x gets really, really small. Okay. And here, as soon as we have a limit like this and we get a number, that's what it means to have a horizontal asymptote. So what's the horizontal asymptote here? 1. And what's the equation for it? X equals 1 or y equals 1? Y equals 1. Right? It's y equals 1 because it's the y values that are going towards 1. That's why. Is HK. Okay. I'm just going to be doing a bunch of examples like this, but any question on this first example? Do you guys see how we're measuring this limit? Right? We're letting x go all the way to the right of the graph, and we're looking at the pattern of y values. We're hoping to detect a pattern. Okay. For x goes to negative infinity, we let x go all the way to the left of the graph, really negative, and we're looking for the pattern of y values and seeing if we could detect a pattern. Right. Now, if there's no pattern, let's say you have a nice wave. We all like sine and cosine waves because you guys all like trig, I know it. What's the limit as x goes to infinity of that? What are the y values approaching? Are the y values going towards anything? Or they just keep bouncing? Right? So the limit would be dne. Right? This one would be dne. Right? So that's not a horizontal asymptote. The horizontal asymptote means the y values have a pattern. If you don't have a pattern, that means you're dne. Yeah. Now, there's another case where if instead of bouncing and bouncing, what if the y values go up like this? And what's the limit? What's happening to the y values? Let's see, Shafial. Infinity, right? The y values keep increasing without bounds. So we would say for this one that the limit as x goes to infinity of f of x, we don't want to say dne, we want to be more precise. We would say it's infinity because the y values are going up, up. Okay. So the y values could be going like up, up, or down, down. Infinity, negative infinity. They could be doing your favorite sine and cosine wave. They could be doing a wave. That means dne. Y values, they don't have a pattern. Right? So when this happens, that's not a horizontal asymptote. Right? But if the y values have a pattern, like 0, or on the left, the y values have a pattern like 1, that's when it is a horizontal asymptote. Okay. All right. Conceptual question. These are the hardest. According to what we defined, what's the most number of horizontal asymptotes we could ever have? Can we ever have a third horizontal asymptote? See, the definition is horizontal asymptote is letting x go to infinity or letting x go to negative infinity. There's no third option. There is no such thing as a third horizontal asymptote. There can only be 2. There can only be 2. Can there be just 1? I mean, we're doing infinity and negative infinity. Could we just have 1? Yeah, Matthew?
Yeah.
Yeah, how? How could we only have 1?
You have 1 if it's not going to infinity.
Or if it's not going to, that's right. We could have 1 when it's not going to infinity, like this one.
Yeah.
And this one might be dne, so there's only 1. Exactly. So if one of the, can we have 0? Can we have no horizontal asymptotes? What would you need to do to make no horizontal asymptotes? Right? Make the right of the graph go towards, let's say, infinity, and make the left of the graph go towards, it's not a number, anything but a number. So you could do something like this. No horizontal asymptotes. Left and right infinity. Sine wave. Left and right D&E. Okay, so horizontal asymptotes, unlike vertical asymptotes, 2 max. 2 max. Vertical asymptotes, is there any limit to how many we can have? No, just make the denominator of your fraction have a bunch of zeros. We'll get vertical asymptotes. Okay, another example. Let's do it numerically. Let's see, f of x equals 1 over x. Okay, we're trying to detect patterns as x gets big. So let's do a little chart. X f of x. X is -1, the output is -1. X is -10, the output is, well, 1 divided by -10, -0.1. -100, the output is -0.01. -1,000, the output is
-0.001.
Okay. We can keep doing it until we detect the pattern, but we kind of have it. So what's the pattern? X is getting really super negative. Where are the Y values going? They're going to 0. They're getting very, they're negative, but they're getting smaller and smaller. Okay. So we could do a limit without a graph. Okay. I guess you can call it the calculator limit. Okay, what about if X gets big? 1, 10, 100. If I plug in 1, I get 1. 10 is 0.1. 100, I plug in 100, we get
0.01.
0.01. 1,000?
0.001.
0.001. What's the pattern? The Y values? Small, are they approaching something?
0.
0 again. So that we say that the limit as X gets super large is equal to 0. Yeah, are we together, guys? So you see it? So here's another example, but we could even do it without the picture. Okay. All right. The mathematical definition, I guess semi-mathematical. Okay. So we say limit as x goes to infinity of f of x equals L if as x increases without bound, i.e. super large, then f of x gets closer and closer to L. Let's say L is not infinity, because if L is infinity, then f of x is just getting really large. Okay. And I guess in parentheses, might reach L, might or might not reach L. Okay. It doesn't have to be like the drawing that I did. It could reach L. So, right, so you could have L here, and you could have a function that doesn't reach it. Could be like that. Or you could have something like L here, and you could have a function actually reach L. It's perfectly fine. Or it could just be a straight line at L. Okay, reaching or reaching doesn't matter as long as the pattern of y values are getting towards L. Okay. Getting close, hitting it, either way. And then we say limit as x goes to infinity of negative infinity. So same thing, but it's just increases without bound is x decreases without bound. Okay. And then the rest of the definition, but a picture is worth 1,000 words. So what is x going to a negative infinity? What you need to picture is you need to picture patterns like this. The y values are going towards L, but x is on the left side of your graph, right? Those are the really negative values. That's the picture. So, what you could do, x goes to infinity. You should think of like stretching out your right hand to the right of the graph, looking at the y values. X going to a negative infinity, use your left hand where the graph is going stretched out on the left of the graph. Limit laws, they're all the same. Limit laws, same as before. Or it's the same ones that you had in section 2.3. So like if you do the limit as x goes to plus infinity or minus. So when I write plus or minus, it's just saving myself writing. Just means either or, right? It's not and. You can't do it at the same time. It's either or of f of x, let's say times g of x. Then it's the limit of f of x times the limit of g of x. X goes to plus or minus infinity. X goes to plus or minus infinity, etc. 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 Okay. Any questions so far? I'm going to do examples, but these are just the preliminaries. Notice what happened here was what's happening with this. See, I got a zero limit is because the denominator is getting way bigger than the numerator. See, we're thinking of x as like a billion, trillion. What's the biggest number you could think of? Trillion, something bigger, 1,000,000,001. So the denominator is way bigger than the numerator. So that's why we're getting an answer of 0. Now, over here, the limit being infinity, what's happening there is that the numerator is way bigger than the denominator if we're dealing with a fraction. These are functions that are fractions. That's how the y values are going towards infinity. What happens if they're roughly the same size? Okay. What about the limit as x, let's say, goes to infinity, 5x squared over x squared plus 7? Okay. So we're thinking of x as being like a trillion. So if you have a trillion squared and you add 7 to it, 7 doesn't change the trillion squared much. It's behaving roughly like x squared in the denominator. And in the numerator, it's behaving roughly like 5x. Well, it is 5x squared. So that means if we ignore the 7 and we sort of think of like the biggest part of the numerator, 5x squared, and we think of the biggest thing in the denominator, which is just x squared, what would we have left? 5x squared over x squared is 5. So just intuitively, right, when we're thinking of plugging in big numbers, this is, we're thinking of this as behaving like 5. Y values are behaving like 5. Okay, we'll check a couple ways here. Let's say x and f of x. What would a calculator say? Okay, so if we ask a calculator, if we plug in 1, we get 0.625. If we plug in 10, we get 4.67. If we plug in 100, we get 4.996. If we plug in 1,000, we get 4.99965. Does anyone see a pattern in the y values?
Yeah.
They're getting closer and yeah,
Approaching 5.
it's approaching 5. Right? You see that? We could plug in 10,000. We'll get something even closer to 5. So that the limit is 5. Okay. That's the limit. Do we have a horizontal asymptote? Remember, horizontal asymptote means I took a limit as x infinity or negative infinity, and I get a number out. Did I get a number out? Right, so what's my ha? Equation? Good. Y equals 5. Horizontal asymptote. Okay. Now, this is really annoying because if I give you a more complicated function, you know, punching this into the calculator is really annoying to figure out the pattern. We could do this way faster than a calculator, right? We don't need a calculator to do this, right? We could do this way faster, okay? We can solve all of these, any example you could think of. Well, any example that I show you with algebra. You could just do all of them with algebra. I won't say it's a lot of algebra, but we could do this really quickly. Okay. And we just need one little fact. It's a theorem, but it's just a fact. But you just really need this. I'll use this as a, let's say a pro tip. This is what you're going to need. Okay. Is when you take the limit as x goes towards infinity, and you have a number in the numerator and x to the r in the denominator. And r is positive. It's a positive exponent. So if x is getting really large, what you guys need to know from algebra is that a really large number raised to a positive exponent is still going to be really, really large. Okay, so what happens if you take a constant dividing and divided by a ridiculously large number, what will be the pattern? When the denominator gets ridiculously large, what's the pattern?
Go to 0, 0.
Smaller and smaller towards 0. The limit is 0. The limit is 0. And I don't need x to go to infinity. I could actually let x go to negative infinity as well. And the limit will be 0. I'll just put a caveat that as long as x to the r makes sense. What I mean by making sense is because what if r is like a half and I'm taking a square root? So I can't really let x go to negative infinity for a square root. Okay. But as long as the exponent I'm taking makes sense for negative numbers, the limit is 0. And it actually makes sense for complex numbers. We're just not doing complex numbers. So let's just say makes sense, i.e. real numbers. Okay. So either way, infinity, negative infinity, the denominator is getting super large. It doesn't matter what exponent it is, then your limit is going to be 0. Right? This is what you're going to be using. Okay. This is all we need. Okay. Okay, so how are we going to use that? Let's say this problem. Let's go back to this problem. So that the limit as x goes to infinity, 5x squared divided by x squared plus 7. Okay. Right. What's really going to dominate is the x squared in the denominator and the x squared in the numerator. Right? Those are the biggest degrees. So the trick is you multiply numerator and denominator by 1 over x to the r, where r is biggest degree you see in denominator. It works for numerator as well, but just to keep it consistent, denominator. Right, so biggest degree means you're looking at the polynomial, or not always going to be a polynomial, but you're going to look at sort of the biggest term in the denominator, right? So what's the biggest, x squared or the 7?
Squared.
It's the x squared. So what we're going to do, we're going to multiply the numerator by x squared. And we're going to multiply the denominator by, 1 over x squared. We multiply the numerator by 1 over x squared. We multiply the denominator by 1 over x squared. Okay. Look what happens. We get that the limit as x goes to infinity, what's 5x squared over x squared? 5. So the numerator becomes 5. Okay. Now let's look at denominator. I have x squared times 1 over x squared. What is x squared times 1 over x squared? 1. And what about, and now I have to distribute 7 times 1 over x squared. So I can't cancel that. It'll be 7 over x squared. Okay. But now I have my limit laws. Okay. Okay, so let's go here. So my limit laws means I could do each piece separately. I could do the limit of 5 separately. I could do the limit of 1 separately. I could do the limit of 7 over x squared separately. That's what my limit laws tell me, that with this algebra, I could do the limit of each one separately. As x goes towards, actually, I could even do plus or minus infinity. It doesn't matter in this case. We'll see later where it will matter, but here it doesn't matter. Now, what's the limit of a constant? What are the y values doing? X goes towards infinity of a constant. It's the limit of 5. What kind of a graph is that? Horizontal line. So the y values are 5. They're always 5. So the limit is just 5. Right. What's the limit of 1? 1. Now here's where we're using our trick. What's the limit of 7 over x squared? Narasota? 0. You see that? Right. The biggest things, which were the 5, they stayed, and the 1 on the bottom stayed. The 7, which was too small compared to the rest, became 0. So what's the final answer? Yeah. So the limit is 5, but in terms of, yeah, what's the horizontal asymptote? Yeah, horizontal asymptote, y equals 5. Conceptual question. How many horizontal asymptotes are there? 1 or 2? See, notice how I did, I said both the positive and negative infinity, whether you do positive or negative. So the positive infinity limit will be 5. The negative infinity limit will also be 5. So there's only 1. There's only 1. So both limits are the same. So we only have 1 horizontal asymptote. Just 1. Yeah, so Rachel, we'd have 2 if the positive limit was, let's say 5, and the negative limit was a different number, like 6, then you would have 2. They're both 5. So in terms of what would a graph look like? 5. Well, I don't know what happens in between, but I could calculate that this function is below 5 for x values, but they're approaching 5 from the right, approaching 5 from the left. So small x values, y values go to 5. Large x values, y values are going to 5. Okay. Okay, question on this. So this is the trick you're going to use. Let's see. We have Sanjita. Yeah, so 7 over x squared is 0. Good. That's our pro tip. That's our theorem. That if we take the limit and the denominator gets super large, we get 0. So just from algebra, 7 over x squared means x squared is a massive denominator. So it's 7 divided by 1 billion squared. 7 divided by 1 trillion squared. So when you're dividing by a more massive number, you're going to 0. Yeah. It's going to 0 because you're dividing by a much more massive number. Yeah.
Another example?
Yeah. So we'll do another example. But this one okay, guys? Yeah. You'll keep using the pro tip. Yeah. Oh, because the limit of 5 is 5. Just because if I have the function y is equal to 5, it's a horizontal line. So then if I look at x going to infinity, what are the y values doing? They're 5. Yeah. Negative infinity, 5. Yeah. And actually any limit that we take, not even positive and negative infinity, x goes to a, the limit of a constant function will just be the constant. I could even write that down. Limit as x goes to a of a constant is always a constant. So a could be A is equal to a number. A could be infinity. A could be negative infinity. A could be, 2 from the right, 2 from the left. It doesn't matter. A constant stays a constant with limits. Question? Yeah.
Instead of multiplying by 1 over x, can't you just divide the point, please?
By what though?
Since the numerator and denominator are the same power, could you divide just like 5 over 1?
So that would be like a little shortcut. Yeah, we'll get to the shortcut in a moment, but that's the idea. That's essentially what we're doing. It's essentially what we're doing is this division sort of trashes, throws in the junk pile all the smaller terms, makes them go to 0, and keeps the biggest part, 5 and 1. Yeah, Jackie?
Do you always have to do the limit to plus and minus infinity?
It depends what the question asks. Yeah, so the question will say plus infinity or it'll say minus infinity. Yeah, so it'll be specific. It'll be specific. But if the question asks like find horizontal asymptotes, then you have to know for yourself, I have to do a plus infinity limit and I have to do a minus infinity limit to figure out the horizontal asymptotes. But if it's just a limit, it'll specify plus infinity or minus. Shariful, you had a question? Question. Okay. All right, more examples? Fine, let's actually do a more intuitive one without the algebra. Let's see, most of these will have the algebra, but let's do one where we're not doing any algebra. Let's do x goes to negative infinity of x plus 1,000. Now, what's the limit as x goes to negative infinity of x plus 1,000? So you have to think about the pattern. If x is like negative a trillion, well, negative a trillion plus 1,000, negative 100 trillion plus 1,000. Where is it going to? What's the pattern? It's going towards negative infinity. Notice that the 1 plus 1,000 doesn't make a difference for us, right? Negative infinity plus 1,000 stays negative infinity. Okay, so then the answer would just be negative infinity. Right? You don't really have to do algebra for things like that. Another example, let's say limit as x goes to infinity. Radical 2x minus 7. Let's think about it. Let's think of it as like x being infinity. So infinity times 2 is still infinity. And if you take infinity and you take away 7 from infinity, what are you going to have? It's still infinity. And when you take the square root of infinity, what is that? Still infinity, because you're taking the square root of larger and larger numbers. They still are growing. They'll grow. So it's infinity. Okay. So if you get to points like that, you don't need to do any algebra. You just have to realize that your numbers are really small or your numbers are really big. Let's do another example that you guys could try. Okay, so remember the trick. Use the biggest degree in the denominator. Let's do limit as x goes to infinity. 4x squared plus 2x minus 3. 9x squared minus 7x plus 2. Okay. Maybe someone could start off the class just by looking at the denominator. What's the biggest degree? What's the biggest x power we see? Squared. X squared. So numerator and denominator, what do we multiply by? 1 over x squared in the numerator, 1 over squared in the denominator. In algebra, we're allowed to do that because it's same top and bottom, so they just cancel the one. So try it, and then I'll do it at 3:35. So if you need to take a break, take a break. But try that algebra for yourself. Then I'll do it. Yeah. Is it for that limit problem? Oh, for this one. I sent you. Oh, that's good. That's good. Yeah. Forget it said this sent the second part, so I got like a 7.5. I forgot to send it. I did it, but I forgot to send it. That was so stupid. I said two students are on iPad instead of student. I felt so dumb. I was getting comments. I can't.
It's easy to it's really normal. Yeah. There's no, there's no, no, is it? How about you entertain us, to be honest? Like, okay, wait. We're like, what's two, three, two.
Yeah, labs.
Open it right now. Infinity. You got it, okay,
Okay, just show of hands. Who is able, don't say the answer, but who is able to get the answer all the way? Who's getting stuck somewhere along the way? The algebra? Okay. Who wants to try putting this in a calculator? Plug in 10, and plug in 100, then 1,000. Okay. Have a lot to plug in. Okay. So let's go through this. So the numerator gets multiplied by 1 over x squared. So what should I have in the numerator? 4x squared over x squared is 4. 2x over x squared, if we simplify that, is 2 over x. 3 over x squared, can we simplify? Oh, minus 3 over x squared.
really?
So limit as x goes to infinity. Okay, what about the denominator? What do we get?
9.
9
7.
minus, what do we get? 7 over x plus 2 over x squared. Right, so now we could do every single piece separately. Okay, what happens to, what's limit of 4? Constant is a constant. Limit of 2 over x, using the pro tip, 0. 3 over x squared, pro tip, 0. Because that denominator's really large, right? 3 over x squared is 3 over a massive denominator. 7 over x, going to 0. 2 over x squared, 0. What are we left with? 4 over 9. Okay, do you guys see how we get that? 4 over 9. Right, a lot of algebra. Right? It's an algebra class. Algebra course, yeah.
You get the zeros.
How do you get the zeros? Oh yeah, the pro tip. See, the limit of a constant divided by x to a power, the denominator is really, really large, and the numerator is staying constant. So you have a constant in the numerator, but the denominator is getting really large. So we know that that's 0. So that's the pro tip. So we get to use the pro tip each time we see that. Yeah. So 2 over x is going towards 0. 3 over x squared is going towards 0. Yeah. Okay. So this is what happens when the numerator and denominator are roughly the same size, right? They're both biggest degree is x squared. That's what happens when they're roughly the same size. Okay, questions on this?
You just leave it like that.
The answer is 4 9ths. Yep, 4 9ths. Is there a horizontal asymptote? What is it?
4 over 9.
4 over 9. Y equals 4 over 9. Okay. Keep practicing with that. Okay. Let's do another example. Let's use the back of the pages, not to waste paper. Another example. Now watch what happens here. Limit as x goes to infinity, x to the 4th minus 2 divided by absolute value of x cubed plus 1. Now, notice this one's a little bit different. The numerator, the biggest is x to the 4th. The denominator, the biggest is x to the 3rd. Right? So really, the numerator here is really a lot bigger than the denominator. Like 4 versus 3, but if you're thinking about like a trillion to the 4th and a trillion cubed, 4 versus 3 is a big deal. It's a trillion times more. Yeah, Matthew.
Well, I remember like the rules. Let me use the one that's in the denominator.
That's right. We'll use the one. Here we're just relying on intuition, but I'm going to use that rule. I'm going to use that rule. But intuitively, if the numerator is way, way bigger than the denominator, what do we expect? What happens when the numerator is way larger, getting larger and larger than the denominator? Is that a big number or a small number? Big number that's getting bigger and bigger. Right, so we are expecting the limit to be infinity. Right, we're kind of expecting it. First thing we need to deal with, absolute values. We don't like them, right? Okay, but remember, x is going to negative infinity, so that means x is positive values. So what's the absolute value of a positive value? Positive. So you just get rid of it. So x going to infinity, x to the 4th minus 2, x cubed plus 1, right? We can deal with absolute values because we're dealing with positives. If it was x going to negative infinity, well, then the absolute value of negative numbers, to turn them positive, it multiplies by a negative sign. So we would have had a negative sign. That's what an absolute value does. Turns negatives into positives. Okay, biggest term in the denominator, what is it?
X third.
X third. So try that. I'll give you guys a minute. X third, numerator and denominator. Try to do the algebra the same way we did before. Okay. Take a moment.
Does it make you happy? It was like for me, like I never look back at my notes. Same thing as that. Okay, that's right.
Okay, so let's try it. Okay, I'll call on somebody. Let's see, Richard. Richard, what would you do for the algebra in the numerator? So x to the 4th minus 2 and 1 over x cubed. So what do you get when you multiply that out? So let's see, x to the 4th over x cubed is just x. And what about minus 2 over x cubed. Can I simplify that? X cubed. I can't really simplify that. So it's minus 2 over x cubed. And what about the denominator? What's x cubed times 1 over x cubed? Just 1. And what's the rest of the denominator? What do I get? Good, 1 over x cubed. And let's take care of the easier ones. What's going to happen to 2 over x cubed? What's the limit of that? Yeah, Richard? Using our pro tip. The pro tip. What does the pro tip say about this? Yeah, right. A really large denominator, massive denominator, is going towards 0. What's 1 over x cubed? Massive denominator is 0. Pro tip. Yeah, Layla? Yeah, Layla, is that what you were going to say? This one? Okay, you see how we're doing the pro tip? Every problem. Okay, it's a theorem. Okay. But what about limit of 1? Just 1. What about limit of x, though? Infinity. It's infinity. So limit as x going to infinity, limit of x is just infinity. The rest, you have 0, 0. So you get infinity. Okay. Yeah. Does that make sense, guys? See how we do that? So it's the same algebra, but it's not going to be a number just because the numerator is way bigger than the denominator. It'll end up being infinity or negative infinity. Okay. You're getting big numbers that way. Okay. Any questions on this? Yeah, you guys see how we did it? Makes sense? Yeah. Okay. What would happen if I made it negative infinity? If I made it negative infinity, well, then I would have absolute value of negative numbers, right? So to turn a negative into a positive, I have to multiply by negatives. And what happens when I cube a negative? Negative. So if it was negative infinity, what you guys would have to do when you see these, you'll have a negative. That's how you have to figure out a way to get rid of the absolute values by figuring out the absolute values are positive. What's inside is positive or negative. Okay, it can only be one of the two. Won't be 0. So if that becomes a negative, then what would happen here? This 1 would actually have to become a minus 1. And what's infinity divided by? So then,
Negative infinity.
so negative infinity. So now we have negative infinity. So numerator is negative infinity divided by negative 1. We still get positive infinity. It turns out we would still get, Rachel, yeah.
Again, how you get rid of the absolute value.
Oh, the absolute value? Well, it's what you guys learn in pre-calc, that the absolute value of x, well, it's just x if x is positive, right? But it's negative x if x is negative. Yeah, so that's what we're using. So if x is going to negative infinity, that means it's a negative value. That means the absolute value is negative x. And we're cubing a negative, so we're getting a negative. Okay. Okay, shortcut. You could use a shortcut if you like. Shortcut. If you're doing the limit as x goes to either positive or negative, either one. But you're lucky enough, as in these situations, to be a polynomial divided by polynomials. So polynomials. Numerator is a polynomial, denominator is a polynomial. What you could do, a little shortcut, is the limit as x goes to infinity, positive minus infinity, biggest term of P1 divided by biggest term of P2. Now, what do I mean biggest? I mean the dominant, meaning the biggest degree of the x is what dominates. So as an example of the shortcut, I could do it for this problem. So that the limit as x goes to infinity of x to the fourth minus 2 over, let's say, negative, I guess I did positive the first time. So let's just do positive. Okay. Infinity x to the fourth minus 2 divided by x cubed plus 1. Okay, now the shortcut means I could take the biggest part of P1. What's dominating P1? X to the, let's even make it interesting. Let's make it like 3x to the fourth and 4x cubed. What's dominating P1? 3x to the fourth. So you're going to have to use 3x fourth. What's dominating P2? 4x3. Okay. So you could do that instead, and that'll help you simplify it. So it'll be limit as x goes to infinity. So it'll be 3/4 x to the fourth divided by x cubed is x. So what's 3/4 times infinity? Infinity. Okay. So you could use the shortcut if you wish for the polynomial over polynomials. Right, those are the rational functions. Okay. Save you algebra. Okay, another example is the one we did. What would happen if we used a shortcut on the previous example? Let's go to, let's say, negative infinity. 4x squared plus 2x minus 3 divided by 9x squared minus 7x plus 2. So we did this one. It took a while. We did it. What would happen if you use a shortcut? What's the biggest? Yeah, what's the biggest in the numerator? Right. What's dominating? It's the 4x squared. It's way bigger than the rest of the numerator. Okay. And you're thinking of like plugging in a million. What's dominating the denominator?
9x.
9x squared. So if you use the shortcut, limit as x goes to negative infinity, 4x squared over 9x squared, then what? X squareds cancel. We get the 4/9. So what the shortcut is doing is it's doing all the algebra for you with the pro tips included. So feel free to use it.
I have a question. So like, let's just say it's like 4x squared plus 7x minus 3.
Yeah.
You know, like the 7 is bigger than the 4.
Oh, yeah. Yeah. Let's make it even better. 10 billion. That billion? Nah. Billion. 10 billion times x. What's going to dominate? 4x squared or 10 billion times x? 4x squared. Because x is going towards a trillion. And then 20 trillion, 100 trillion. So it will eventually overtake. Yeah. Yeah, good question. Yeah. For polynomial over polynomial, yes. Yeah, it always works for polynomial. So that you could prove that polynomial over polynomial, you just do the trick that we did by the denominator, and you'll just end up with this.
I only posted a velocity for
Velocity?
tangent velocity.
Yeah, it should get updated. I don't think it's updating correctly, but that one's going to be due like next week at some point. Yeah, that's going to be the lesson for Monday, and then be Wednesday.
Is there like a day that you think the test will be?
Right now, it's looking like I'll put out an announcement, but we have 2 more sections after this one. So,
Yeah,
we need 2 more sections. It'll probably be Wednesday, October 11th. Yeah, I'm gonna set an announcement, but that's what we're set right now. Wednesday, October 11th. But you'll have a practice exam, all that. We'll review in class. Okay, good. Any questions on the shortcut? Who wants to use the shortcut? Right. Who wants me to prohibit the shortcut? You can use the shortcut if you want. You might as well know it, just because like when you do Calc 2 and 3, they'll have limits like this, where they'll expect you to do it really fast. So you might as well know how to do it very fast. They come up. Okay. But that doesn't mean every problem can be done with a shortcut. That's only polynomial over polynomial. Let's do another example. Do another one over 11. Limit as x goes to infinity, 2x minus 7 radical 5x squared minus 3. Yeah. So the denominator is not a polynomial, right? So not everything's a shortcut. Yeah. Matthew.
We make it a polynomial.
Oh, good. I should address this because so many students love to do this. Might as well nip it in the bud. It never works because students that do this will keep doing this for the rest of their lives, and I can't stop it. But maybe I'll try. Maybe I can help one of you right now. Okay, students will love to do this, and it's totally forbidden. Why is it forbidden? Because it's not true.
Oh, I didn't mean that.
This is wrong. You can't. Oh, how do you make it a polynomial?
I was gonna say, like, if you square it on the top and the bottom.
Square the top and oh, you can't. That'll change the function though. Yeah. So squaring top and bottom changes the function. So we can't change the function. Squaring would only work is if you had an equation. If the top and bottom is equal to, like, let's say a constant like 3, then you're right. I could square both sides. But that's because I have an equation squaring both sides. If I square top and bottom, I've changed the function. I can't do that. Okay, but at least it reminded me, don't do that. It's forbidden because it's wrong.
So can this square root can you like a parentheses 5x squared minus 3 or minus c to the power 1/2?
Oh, you mean like 5x squared minus 3. This is true. Yeah, because the power 1/2 means a radical.
-1/2.
Yeah, the power 1/2 means a radical. Yeah, I'm just trying to stop students from doing this because I know you're out there. But I can tell just by their face if they do this. Okay, I can't tell by the face, but I will see on the exam. Please don't do that. It's not true. It's just not true. Just, plug in a value of x like 2, and you'll see that both sides are not equal. It's just not true. Students will start saying like x squared plus 1, square root is x plus 1. It's not true. It's not true. It's forbidden because it's not true. Yeah, Jackie.
Since there was a rule for if the one, is there a rule for when the exponent is negative?
Well, the exponent is negative. You don't really need a rule because just algebra lets you flip it and put it into the numerator. So if I had like 1 over x to the negative 3, that's the same as x cubed. So I could always take negative exponents and flip them to positive, just using algebra. So I don't actually need a rule. I could just convert negative exponents to positive by taking reciprocals, which is what you could do in algebra. Okay, we have to resort to the trick, right? So we are going to use the trick of biggest term in the denominator, but we have to think very carefully what's the biggest. The biggest is not x squared. That's what we have to be careful. So what's the biggest in the denominator? It's not exactly x squared because there's a radical. What is it really?
X.
We don't want constants. We don't care about constants.
X.
It's x squared, but with the radical. Yeah, Matthew.
X.
It's x, exactly. Yeah, it's x squared with the radical. So our trick still works. We just have to realize that because of the radical, we have to do top and bottom by rad x squared. That's the biggest in the denominator. Oh, 1 over, sorry. No, 1 over rad x squared in the numerator, 1 over rad x squared in the denominator. And now watch carefully, guys. This is where those that struggle with algebra are going to have a tough time on these. I think the WebAssign, a lot of them are like this. So watch carefully. First of all, do you see step 1? The biggest thing is not x squared, it's rad x squared, right? Because this could be thought of as radical x squared, giving you sort of the biggest term. Now, in terms of doing the algebra, well, the numerator, limit as x goes to infinity. The numerator, I might as well do 2x minus 7. And like Matthew was saying, radical x squared, I might as well turn it into 1 over x because that makes it easier. That's for the numerator. That doesn't mean it'll be easier like that for the denominator, but for the numerator, yes.
1 over absolute value.
Good, actually, great. Safael is saying absolute value of x. That's actually more correct than what I wrote. I skipped a step. Why is it? Why am I allowed to make it 1 over x?
Because positive.
Because positive infinity. That's right. That's right. Yes. Very good. Yeah. If it was negative infinity, that's right. It would be absolute value of x because see, x squared is positive, radical x squared is positive, so I get absolute value. If it was negative infinity, it would become a negative x to make it positive. Good. Divided by, now, both of these are radicals. So your algebra teacher that you have talking to you in your head is telling you, keep these as radical, right? Radical over radical lets you combine radicals. And it becomes 5x squared minus 3 divided by x squared, all under the radical, right? When I'm dividing by radicals, I can make everything one radical, right? Algebra rule. Algebra rule. Right. Right, so it's algebra class. Back to algebra. Limit as x goes to infinity. How do I simplify the numerator? What do I get? What should I write? 2x divided by x is 2 minus, what should I write? 7 over x, which can't be simplified. Good. Now the denominator. Now I could do both pieces. 5x squared divided by x squared is 5. And then I also have to do the second piece. Many students forget to do the second piece. Minus 3 over x squared. That's the algebra. Okay. I haven't even started any limit, right? All I did was simplify. Okay. Okay. Now I could actually take limits. Limit of 2 is limit of 7 over x. Pro tip, 0. Okay, now the square root operation is continuous. One of our limit laws means I can go inside the radical with the limit. So what's the limit of 5? 5. Yeah, 5 or the whole thing. Limit of 5 is 5, but the whole thing would be with the radical, yeah. What about 3 over x squared? Limit of that is 0. Right, so what am I left with in the numerator? I have 2 in the numerator and the denominator, radical 5. Radical 5, yeah. See, Layla?
I just had a question on, like, for the numerator, why are you multiplying by 1 over x and not like 1 over radical x squared?
I simplified it, yeah, good. I simplified it. Yeah, so it is radical x squared. So that's how I started, right? But the question is, I still want to simplify 2x minus 7 times 1 over radical x squared. So to simplify it, it makes it easier to turn radical x squared into an x. Because then I could simplify it. Otherwise, I wouldn't really be able to simplify. Okay. So it helps me simplify it to this form. But I did start with radical x squared. And as Raphael pointed out, radical x squared is really absolute value of x. So watch out for that. So the reason I was able to turn it into x is because x is positive. Okay. So you have to use all these little algebra tricks you have to deal with absolute values, to deal with radicals, all of that. Okay, yeah, question on this. Okay, this is how you guys are going to deal with the radicals. Okay, if f of x is continuous, here's a little trick that you guys could use. If you're doing the limit of a composition, x going to positive, negative infinity of f of g of x. So you guys will see some oddball questions like this. And when you see a composition like this, you could put the limit on the inside. That's what continuity lets you do. Okay. So it looks weird when I write it in a formula, but as an example, it's not so bad. What it means is if I have x going to infinity, e to the 7 over x cubed, what it means is I could just do, this is the composition of two functions, e to the x and 7 over x squared. I could just do the limit of that exponent, right? So what's the limit of 7 over x cubed? Pro tip. 7 over x cubed goes to it's x 0. So what's the final answer? Right. E to the 0 is equal to 1. Yeah, so do you guys see that? So if you see something weird with e's or ln's or signs, that's what they're trying to get you to do. Okay, it's doing the limit of the inside. Okay. So what we basically did is this is the limit of 7 over x cubed. That's the idea. So our final answer was 1. Let's see. Let's go over some more oddballs. Another example. Limit as x going to infinity of sine of x. Sine of x keeps oscillating up and down, up and down. DNE. Yeah, why? What's gonna happen to the y values if x gets large? Just random. Are they approaching anything? No. Okay. So you'll have to treat these oddballs where we don't have the tricks. So the trick helps you deal with the more complicated problems. But these kinds, you have to use more of your intuition. Similar limit as x goes to infinity of ln of 3x squared minus 7x plus 9 divided by 2x squared plus 8x. Okay. So again, similar thing. Ln is a continuous function. So I'm dealing with the composition. I'm allowed to do just the limit and put it on the inside. So I could keep the ln on the outside, and I could just do my limit on the inside. 3x squared minus 7x plus 9, 2x squared plus 8x. Yeah, Matt. Yeah.
Can you do the trick, the 3x squared over 2x squared?
Good. Yeah, now I could do the trick. I could use the shortcut. The biggest thing in the numerator is
3x squared.
3x squared. Denominator is
2x squared.
yes. This is the biggest I see in the numerator. It overpowers the denominator. 2x squared overpowers the 8x. Yeah. What would I be left with? 3x squared over 2x squared is 3 over 2. So my final answer, ln of 3 over 2. Okay. So, do you see what I mean by the composition? Yeah, the composition of limits lets you put the limit on the inside function. Yeah. That's the idea. Okay. Okay, you guys getting the hang of how we're doing this? We've covered a good chunk of trying to cover all the crazy things you might see on the website. I think we're covered a good chunk. Okay. Now let's see if we can putting together. Now let's put in together all of sections 2.1 all the way up until now. Okay. So we can combine everything that we did. Now that we have every kind of limit, we can combine them all to answer, to figure out how functions look, how to graph functions. So x squared plus 7x plus 10, x squared minus 25. Okay. Now we can sketch a nice graph. Okay, now we can sketch a nice graph. Okay. We're going to put everything we did together. So part A, domain. We have to remember, what is the domain? We have to watch out for. What's the domain, Alyssa? That's right. Anything except 5 and -5. Okay. Vertical asymptotes. This is a hard question. Right. Also, you have to take limits on each side. Okay. So vertical asymptotes are going to be all your C/0 cases. Okay. So the way to find vertical asymptotes is we see when our denominator is 0. When is our denominator 0? 5 and -5. Okay. So it might be a vertical asymptote or it might be a hole. Just depends if it's C/0 or 0/0. Okay, so we have to figure that out. So that's why you'll have to take limits. You're gonna have to test every single case. X goes to 5 from the left. X goes to 5 from the right. You'll need to do X goes to -5 from the right and -5 from the left for every single case. Okay. And it'll help you to factor. So we could factor this. Let's see, X plus 5 times what? What's the factor in the numerator? X plus 2. And how do we factor the denominator?
X plus 5, X minus 5.
Right. X plus 5, X minus 5. Okay. So it'll help you to factor these out. So this one, X plus 5, X plus 2, X plus 5, X minus 5. And we'll have to do X plus 5, X plus 2, X plus 5, X minus 5, 5, X plus 2, X plus 5, X minus 5. Okay, so we'll have to figure out each case. Let's plug in 5. What do we get if we plug in 5? The numerator is 5 plus 5 is 10 times
C/0.
7, which is 70 divided by denominator is 0. Okay, so you have to show this kind of work. You can't just write an answer. You have to show this kind of work. So this is C/0 case. 2 options. What are they? Jackie? Good. Positive or negative infinity. That's when we divide by 0, that's what happens. Okay. How do we decide if it's positive or negative? How will we know? Matthew?
Plug a number going to 5 from the left in the denominator.
Good. So we'll plug in a number like 4.9. So then the numerator is positive. And 4.9, the denominator is going to be positive or negative. 4.9 minus 5 is negative times a positive, which is negative. So the total is negative. So it's minus infinity. Okay. What about this one? If I plug in 5, what do I get? Same thing, 70/0. So the answer has to be positive or negative infinity. Right. So positive or negative infinity. And how do I test it? I plug in like 5.1. So I get a plus in the numerator. And then a plus times a plus, which is plus. Positive infinity. Put a question mark here because we don't know. Okay, what about this one? Limit as x goes to -5. The numerator is 0. The denominator is 0. That means we have to do algebra. What's the algebra that we need? right? We cancel. And what do we get? Plug in -5. Numerator becomes -5 plus 2, -3, divided by -10. Okay. Same thing, -5 from the left. It's a 0 over 0 case. We plug in -5, and we get -3 divided by -10. Okay. After all that, now we could answer, what's the vertical asymptote? How many do we have? Yeah, Rachel.
X equals -5.
Right. X equals, what's the vertical asymptote? Let's see. Well, -5 did not lead to infinity. Right. Vertical asymptote means we have to be led to negative or positive infinity. So X equals 5. Right. Is X equal -5 vertical asymptote? No, right? We had a limit that was not infinity. It'll look like a hole. In order to draw this, it'll have to be a hole. Because it's undefined at -5. It's not in the domain, but we do have a limit. Vertical asymptote is like that. And then part C is going to be horizontal asymptotes. And that's what we learned today. Okay. And how do we check for horizontal? We have to take a limit as x goes towards infinity and negative infinity. So you guys are going to have to do a limit as x goes to infinity. This one's easier not to simplify. X squared plus 7x plus 10 over x squared minus 25. And then limit as x goes to negative infinity. X squared plus 7x plus 10, x squared minus 25. Okay, so for something like this, it's really nice to use a shortcut. Biggest thing in the numerator is, what is it? X squared. The denominator, what's the limit? Right, limit is going to be 1. And what about the bottom one? Right, it's still x squared over x squared. How many horizontals?
1.
1. What is it? Y equals 1. Okay. So part D, now we could sketch the graph. Now, this is the trickiest part, but try it, guys. Try it first. See if you could sketch it. You have a vertical asymptote at 5, negative infinity to infinity, left and right. See if you could sketch that. Try to start with sketching the vertical asymptote, which is 5 left and right. Then start sketching the hole at -5, right? Because we did a limit at -5. We got 3/10. We could draw that limit where the limit is 3/10. So start sketching something that satisfies this. And then you could add the horizontal asymptotes afterwards. Then you can put the horizontals into your sketch. So try it before I do it. You'll have to know how to sketch it on your own. vertical, 5. Here's 5 was vertical, 5 from the left going towards negative infinity, 5 from the right going towards positive infinity. Was able to get at least that far. You guys able to at least draw something that looks along those lines? Okay, now you need a limit at -5 where the limit is 3/10. So here's 3/10. Okay, but it's undefined at -5. So limit of, right? When you have a limit left and right's match, you get a drawing like that. Okay. So that's those pieces. Okay. Horizontal asymptotes, x going towards infinity, the y values are heading towards 1. So here's what maybe I'll do it in a different color. This part is in red. So to draw this part, what I need to do is I need to sketch something going here, like that, at 1. Then maybe I'll do it in blue. So this part, x going towards negative infinity, the y values are going towards 1. So I have to do x is negative infinity, y values are going like this. Something like that. And then sure enough, I could connect them. So there it is, -5 and 5 are not in the domain. But this is what a vertical asymptote looks like versus a 0/0 limit, which leads to a hole. And check your calculator, see if you get something similar. Should be. You might even be able to see the hole in the calculator. I think it's like you kind of see a little gap where you're wondering, why did the calculator run out of ink? There's nothing there. No, it's calculator, it's a gap there. It's undefined there. That's the hole. Okay, questions on this? Yeah. Okay. I want to be able to combine each part. Let's see.
I'm kind of confused about limit and isopages.
This one?
Yeah.
5 from the left. Oh, why was it negative infinity?
But when you lost it, like, it can't pass through the asymptote, right?
Yeah, it's just the asymptote. See, it's undefined at 5.
Mm-hmm.
So the graph can't go through x equals 5 because it's undefined there. But we're saying the y values when we took the limit are negative infinity. So then the y values have to get really, really negative.
From the right side.
Oh, from the right side. So that's this limit, 5 from the right. And we computed plus over plus, it was plus infinity.
Mm-hmm.
So that means the y values, as we approach 5 from the right, they have to go to really large plus infinity. This plus infinity.
And it doesn't like go below the horizontal.
Oh, so that part I just knew in advance that it doesn't. But theoretically, if we just had limits and I told you to sketch and somebody sketched like, oh, it goes below and then above, because we don't really know what happens in between. But then like this, I'd still get full credit for that. Okay, because we just don't have enough information to fill that in. But we'll have tools later in the class to fill that information. Yeah, so you're right. I made it not cross just because kind of cheated. But from in terms of giving like a little sketch based on what you guys knew, anything like this would be fine. So the horizontal asymptote is still at 1 because what happens in between, we don't know. But as x goes really large, the y values go towards 1. Yeah, so that's a good question. All right. Other questions? Anyone here that I'm missing? No. Okay. Okay, so let's look. Try to open up your WebAssigns. You could, if not, you could look at mine. Okay, so this is going to be 2.6. Okay, some of them are just conceptual questions. Number 2, look at like number 2 as x goes towards infinity. So this is a good kind of question just by looking at what's the limit as x goes towards infinity? What's the pattern of y values? -2, right? So you need to be able to look at a graph and figure these out. Number 3, you have to do your own sketch. Pretend, guys, that it's not multiple choice. When you do questions like number 3. Same thing with number 4. Pretend it's not multiple choice. And then eventually it'll get to the algebraic ones. So I want you guys to at least try the radicals. So try number 9 and 10. And I'll come around and check and see who's getting stuck. If you guys can work together, and then I'll come around a little bit.